Now, just to prove that everything always happens together and that you need to keep building on those ideas, we have a combination problem that will involve both constant velocity and constant acceleration. And it's going to be our job to figure out when to use what and why. So here we have the Apollo 11 spacecraft, and all these numbers are completely made up and no research was done. So giant caveat there. But says the thrusters of the Apollo 11 spacecraft had to ignite their thrusters, that's just redundant, for 10 seconds and then shut them down. All right. Their initial speed was 200 meters per second, and their thrusters would accelerate them at 13 meters per second squared. How far will they have traveled in the 15 seconds after the thrusters were fired? All right, so I often like to draw some pictures and then make some graphs and kind of go from there. So let's do that. So let's go back and revisit some key statements here. So we've got our spacecraft. Look at that spacecraft. Look at the art class. It's really paying off these days. All right, so they're going here with an initial velocity of 200 meters per second, and then they fire the thrusters. Sound effects professionally added. And we want to say that, okay, this happened for 13, this adds an acceleration of 13 meters per second squared. So this is our initial velocity. And this happened for 15 seconds. All right. And so eventually they'll get over here, and then we want to know what's going to happen after that. So we want to know how far are they going to go after those thrusters are turned off. Well, while the thrusters are on, we definitely have acceleration, and while they're turned off, well, everything in our space just kind of cruises along at a constant velocity. So off to the side here, I'm going to draw myself a little velocity time graph just to help guide my understanding of what's happening here. So initial velocity was 200, and then I am speeding up. All right, and then once I cut the thrusters right here, then I'm going to cruise along at a constant velocity. So I choose to try and then I want to know what is this displacement, and so I know that's the area on my velocity time graph. So if I can figure out what this area is, then I can figure out how far I went. So first of all, it looks like to solve this, I need to know the time. Well, it was 15 seconds after, so this time period right here is 15 seconds. So I don't think they were on for 15 seconds. I think I made a horrible mistake. Oh man, I think that, oh, it was 10 seconds they turned them on for. Man, why didn't you guys tell me? I'm judging you right now. You should have all told me that I made a mistake. All right, 10 seconds. This right here, this change of time here, that's 15 seconds. Man, thanks for a lot, guys. Made me look pretty stupid. All right, so that's 10 seconds there while we're accelerating, and then 15 seconds we're just kind of cruising along. So it seems like one thing I definitely need to know. If I look at this, well, I'm trying to find the area of a rectangle. The base would be 15. The height would be, I have no idea. So it seems like if I can find this velocity, that's going to help solve a lot of my problems. So let's try and solve that velocity. So I'm going to use my first initial information here, and I'm going to basically just try and solve for what is that velocity. And so I've listed all my givens, and so the equation that's going to get me to victory is going to be velocity equals my initial velocity plus my acceleration times my time. So that final velocity is unknown. My initial velocity is 200. My acceleration is 13. The time is 10. So when I solve for my velocity, let's go to the physics computer. All right, just got the results back from the physics computer, and it says the velocity is 330 meters per second, which, fun fact, that would be then the speed of sound. So apparently we did not break the sound barrier, not that you really could, because there's no material in our space, so whatever, moot point. All right, so now I know this velocity is 330. So if I want to know how far I went, I could just use the area method. And if I want to say that, it says displacement equals area. And so that's the area of a rectangle. So my displacement would simply be my base, which is 15, times my height, which is 330. And so then my displacement will be 4,950 meters. So that would be my displacement. during that second time there. So that would be the answer to my problem. Now, if I didn't want to use the area method, I could then say, well, during this portion, I'm just cruising along, so I'm traveling at a nice average velocity, and the equation for average velocity is displacement over time. So we could say, well, my average velocity is that 330 that I left myself off with, and then my displacement is unknown, and then the time interval is 15. So then I could just multiply here, and I could say, well, do that math. Your displacement is 4,950 meters. Again, confirming the fact that you can do area techniques, or I should say graphical techniques, and they'll be perfectly matched with your any algebraic techniques you'd like to use. So, two ways to solve the problem, but either way you had to realize we had both constant velocity and acceleration. So big thing students make the problem with is if they sketch this all out, they'll often say, oh, the total time is 25. And this is a mistake student make. This is not correct. Do not do this. They'll say, oh, the total time is 25, and then they'll put that into here as their total time. But that's not correct. Can't do it. Don't do it. Just don't do it. Just don't even go down that path. All right? Because we don't have one acceleration during that time. We have two separate accelerations. I know one of them 0, but we have two separate accelerations. And so therefore we have to use two different equations to solve this problem. All right? Hope that helps. And have fun in outer space travel.